Now I want to move on to a really important principle of statistical graphics. Um, it turns out that the human eye follows area much more than it follows length or width. Where our perception is focused on area, and statisticians have worked with psychologists to to learn this fact, and that actually has informed the way we do graphics. The area taken by a graph object should be the thing that changes to demonstrate the quantity being measured. Now, when I'm doing a bar graph, that means a couple of things. One is having bars that are equal width. The bars should each be the same width, and the height is the thing that adjusts. But there are also some things that I should avoid. So I'm gonna mention three: pictographs, 3D charts, and bar graphs that don't start at zero. And I'm going to show you why those are problematic. So let's start with pictographs. And by the way, I'll mention this again. These things do show up in practice, and so we have to be on our guard for them. So here's an example of a pictograph. Rather than using bars, because gosh, bars are boring, I'm going to use this little color palette, and I'm going to show the color choices by making the color palettes bigger or smaller. And you'll notice that I've got the blue color palette, and the top of that color palette goes up to 130, whatever, to 139, and the green one goes up to 88. The top of the green one goes up to 88, and so forth and so on. But what's weird is that the red, looking at this picture, the red palette all the way to the right is kind of small. Compare it to the blue. Remember what we said. Red was about a little less than half of blue. And if you look at that, red looks a lot smaller. And that's because you're than half of blue, and that's because your eye is tracking the area. The red area is actually quite a bit smaller than half the blue area. And you notice that it gets even worse because things like black, which had a fair representation. I mean, it wasn't as popular as blue. It's a teeny tiny thing compared to blue. Okay, and the problem with this is that we've grown the palette, this little picture, this pictograph. Each of the pictures have grown not only in height but also width, because we wanted to keep the scale of the palette the same, and so we increase the height and the width when we're increasing the quantity. And the problem with that is a lesson from geometry, that the area scales by the square of the side length. So just to remind yourself, so if I have a square and then I double its width and length, how much bigger an area is the bigger square? And the answer is not twice as big. I doubled the length and width, but I actually have 4 of those squares, because I get 4 little squares inside there, each the size of the original square. So when I blow up these palettes at the top, I get a squaring of area, and that's going to be bad. Now I actually can use that to my advantage. This is actually a correctly done pictograph where each of the palettes have been grown, but just in the height and the width the right amount, so that you can see that red is about a little bit less than half as big in area-wise as blue, and green, black looks not teeny tiny, but it's small, but it's not teeny tiny, and so forth and so on. I'll tell you what I did is I grew these by the square root of their sizes. One disadvantage is that I can no longer put a y-axis here. The height of the palettes don't tell me how much they are. But in some sense, so even this kind of pictograph has problems. But at least I did it correctly using the area principle. The area of each of these palettes it reflects the quantity that they're measured to. Another thing that can go wrong is using a bar graph with a non-zero bottom. So on the left, I had to pick the 5 biggest colors: blue, green, pink, purple, and red. And what I've done is I've actually started at 20, and you notice at the base of the y-axis it's at 20, and this changes things. You'll notice, what does it look like red is compared to blue? So again, going back to that, we know that it was about a little less than half, but now it looks like maybe even only a quarter. The red area is only a quarter of the blue area. And it completely de-emphasizes pink, right? Pink and purple. Purple is only a third of the size of red. And this is all coming from the fact that I started at 20. If I had properly done it, and that's what's on the right, you notice that I retain the right proportions. The red is half the size of blue. Purple is half the size of red. So those relationships we noticed before are correctly done, but that's because I started at 0. So when I make bar graphs, you must, and I'm not, I mean, you should make bar graphs this way, but you also watch out for bar graphs that are improperly made, where they don't start at 0. You have to start at 0 in order to satisfy the area principle. And then the last thing, this is a 3D pie chart of the color preferences. And I usually joke this is a statistical abomination. This is really bad. 3D charts look cool, but they very much distort what's going on. And I'll just point out that, you know, green was quite a bit less than blue in terms of percentage. And it was very obvious when I did a nice flat pie chart. But with this, the green is actually in some sense emphasized, both because it's at the front and therefore isn't foreshortened. And that is, you know, the perspective makes the things in the back of the pie graph a little bit smaller. So the things in the front seem a little bit bigger. So that's one thing that's making green look big. And then also the fact that green gets this whole front piece of the pie chart in its color kind of overwhelms and makes the green look a lot more than it should. So 3D pie charts are not a good idea. So don't use them. Don't use them. Flat pie charts are sufficient and are not subject to this same kind of confusion. If you ever have somebody who says, "Oh, spice it up with a 3D pie chart," come back to me and I'll argue for you that these are not a good idea to use. I want to show an example, and this is one of my favorite examples of good graphs and bad graphs. And just briefly, this is from an actual news article from 2007 or 2008, and it is about the undersea cables that carry our internet traffic. So the cables are what they call fiber optic, and they span the ocean. You can see in the top part of this the map of the world, the paths which these cables take all over the world, directing our internet traffic from the Americas to Europe and then into Asia. And the reason for this chart was that it had just happened that right outside of Alexandria, Egypt, right where the Suez Canal it starts, a ship dropped anchor and broke one of these fiber optic cables, and the broken cable carried traffic from Europe into West Asia and India and Pakistan and so forth and so on. And so lots and lots of people lost internet for quite a long time, because it's not exactly, you can't just dive down to the bottom of the ocean and plug the two pieces together. You actually have to do some major work to get these fiber optic cables back together. So this news article was talking about this notion of the cable breaking, and in the bottom they had some graphs to compare. So let's zoom in to the one at the bottom left. So oops, this one was this notion that how many people in each of these countries were affected by the Alexandria accident. Now, I will tell you, when I first saw this, I thought, this looks bad, because they're using circles and they're growing the circles. And of course, the way you want to grow a circle is to grow it both in its width and its height. That's going to violate the area principle. But fortunate for us, they actually included the numbers. 60 million from India, 12 million from Pakistan, so forth and so on. And looking at the numbers, what it looks like, so India had 5 times as many people affected as Pakistan. And if I look at the circles that represent India and Pakistan, it does indeed look as if Pakistan is a fifth of the size. The Pakistan circle is a fifth of the size of the India circle. And for comparison's sake, go down to the next level, right? Pakistan to Egypt is a 2-to-1, right? Twice as many people in Pakistan were affected than in Egypt, and the circle for Egypt is about half the size in area as the circle of Pakistan. And so they actually did this right. They actually grew these circles correctly so that their area reflected the numbers that they were trying to demonstrate. But what's interesting is right next door, right? The graph that's right over next to it is problematic. So what this is a representation of the cable's carrying capacity. So these fiber optic cables carry data, and data is measured in terabits per second, TBPS. And it turns out that the companies lay these down underwater, and then they lease to big internet companies like Google or Microsoft. They leased capacity on the cables, but what happens is that Google will buy a bunch of capacity, but not use it all. So the 3 circles here are supposed to represent, the big one is the total capacity of all the cables. The yellow circle is the purchase capacity, how much the internet companies purchased. And then the red circle is the used capacity, how much is actually being actively used. And again, fortunately, they gave us numbers here, 7.1 for the big circle, 5.7 for the medium circle, and 2.1 for the little circle. Now, it's interesting to me that little circle, when I first saw this, I was like, wow, we have this total capacity, the big gray circle, and we're using so little of it, 2.1. I mean, it looks like maybe, I don't know, a tenth or less of what's possible. But if I look at the numbers, 7.1 to 2.1, actually we're using more than a quarter, almost a third of the total capacity. That little red circle is not a third of the big gray circle. And the reason is they blew it. The heights, look at the heights. The 2.1 is about a third to a quarter in height, and the red circle is about a third to a quarter in height of the gray circle. So they grew in both directions, but we're recording the number only on the height. So they were breaking the area principle. So this graph is misleading. It's misleading and can cause confusion, right? I mean, it did for me, really, honestly. This is when I first saw this. I was a little confused about the used capacity. Seemed so little. We're using so little, and yet we're not using all of it, but we're using more than that little tiny amount. So good statistical graphics are important, and bad statistical graphs can be confusing and misleading.